Hello, I'm Catalin Hritcu from the Max Planck Institute for Security and Privacy in Bochum, and I will tell you more about our journey beyond full abstraction, which is a work on exploring various criteria for secure compilation. This is joint work with Carmine, Rob, Deepak, Jeremy, and Marco, as well as a few more recent collaborators. Good programming languages provide helpful abstraction for writing more secure code. Some of these abstractions are so natural to us that we often don't even think about them as abstraction, things like structure, control flow, or procedures, but also things like modules and interfaces, and also higher level abstractions such as correctness or security specifications. However, these abstractions are currently not enforced when compiling the code all the way to machine code and linking it with adversarial low-level code. The problem is that in such cases, all the security guarantees of the source language are completely lost. So to improve on this, we would like to build secure compilation chains which protect these abstractions from the source level all the way down, even against adversarial low-level code. And people have looked at this before. There are various enforcement mechanisms out there trying to achieve some of this, from operating system processes and software fault isolation to capabilities and tagged architectures. But it doesn't matter too much how things work internally. It's usually a shared responsibility between the compiler, but also the linker, loader, operating system, all the way down to the hardware. And I call all of this together the compilation chain, which is trying to achieve security. So the goal is to enable source level reasoning about security. In particular, we would like to know that a linked adversarial target code cannot break the security of a compiled program any more than some linked source code could. So one thing to note here is that this is not about making things perfectly secure, or not a compiler that only produces secure programs. However, it shouldn't be the compiler that introduces bugs. If there are attacks, they should also exist in the source, which means, well, we should be able to reason about the security at the source level. So we don't want lower level attacks than this. And the way we are proposing to state security of such compilation chain is by preserving security against adversarial context. So if the source program was secure against arbitrary source context, and we compile this program using a secure compiler, we would expect to obtain a compiled program that is secure against arbitrary target context. And the idea here is to build a secure compiler that protects the compiled program enough from the target context, so that the target context has no extra power over the compiled program compared to a source context. So this is the kind of property we'd like, but to make this fully precise, we should also define what do we mean by secure. And in this work, we look at a very broad range of properties that one could try to preserve against adversarial context. So we looked at trace properties, things like safety and liveness, so that bad things don't happen or that good things eventually happen. We looked at hyper properties such as non-interference, so the fact that the data of the program is confidential, for instance. And we looked at relational hyperproperties, which are properties of multiple programs. For instance, that two programs have the same behavior. And then we went and studied many subclasses of such properties and built a big scary diagram. So don't worry, you don't have to understand any of the details of this. All that matters is things higher in these diagrams are stronger criteria, things lower in this diagram are weaker criteria. Usually each criterion corresponds to robustly preserving a certain class of properties or hyperproperties or relational hyperproperties. Arrows that are pointy are strict implications, we have proved. But well, so we have a hierarchy of secure compilation criteria. But one thing to keep in mind is that, well, being higher in this diagram is not necessarily better. And I don't think there is a one-size-fits-all security criterion for secure compilation. It's really a trade-off. The higher you are in this diagram, the more secure you are. However, the lower you are in this diagram, the more efficient you can enforce things, fewer things you have to enforce, and also the easier the proofs become. So for trace properties, all one has to enforce is the integrity of the program against the context. For hyper properties, intuitively, all you have to additionally protect is also the confidentiality of the data of the program. And for relational hyper properties, you also need to ensure the confidentiality of the code of the program, which might be problematic. But anyway, that's why we have a big hierarchy, and you can choose whatever criterion is the best for your specific application domain. Now, I'm going to delve into one single criterion, robust trace property preservation, and explain it in a bit more detail. And it's phrased like this: for any source program P and for any trace property, so for any set of allowed traces, pi, if the program P has the property pi in any source context CS, so if for any source context CS and for any trace that CS together with P produce, that trace should be in the set of allowed traces allowed by the property pi. So if this holds in the source, then we would like that this also holds in the target, so that P compiled satisfies pi in arbitrary target context CT. So this is one of our security criteria, right? Robust preservation of trace properties. And it's a nice property-based characterization that really tells you what you might want to achieve, how are properties, what class of properties the secure compiler preserves. However, it's not exactly what you want to prove most of the time. For this, we came up with a property-free characterization, which looks a bit like this, and which is equivalent. So it says for any program P, for any target context CT, and for any trace that CT produces together with compiled T, and here we are talking a bad trace, so an attack. For any attack in the target, we expect that there exists a source context that exhibits the same attack against the original source program. So this is the way we prove robust trace property preservation. And we have come up with such property-free characterizations for all of our criteria. And the nice thing is that they characterize some of the difficulty of the secure compilation proof. So if you are at the robust trace property preservation, the quantification looks like this of the property-free criterion for all programs, for all contexts, for all traces that exist as CS, as we saw on the previous slide. So in a way, you can use the trace to produce CS. And this becomes very interesting as soon as you move to robust safety preservation, in which instead of a complete, potentially infinite trace, we are looking only at finite trace prefixes, M, and you really have a single finite trace prefix to work with, and you can generate a target a source context CS that really only works for that single prefix M, finite. So this gives you a simpler way to back translate things. And in fact, it generalizes to finite sets of finite trace prefixes. So you can also produce a context that generates a certain finite set of finite prefixes. However, as soon as you get out of this green area on the right, you need to do something else, right? In particular, for robust hyperproperty preservation, from the property-free characterization, you can see that compared to trace properties, these two quantifiers are swapped, which means now you have to produce a context that works for all traces. So you can no longer build your back translation based on a concrete trace. And then at the highest level, we have, well, our strongest criteria in which the two more quantifiers are swapped, the one for the program and the existential, which means now you have to produce a context that no longer depends on the program and can only depend on the target context CT. So this gives you a feel for the kind of back translation proofs you can use to produce this source context, depending on where you are in our big diagram. So in this journey beyond full abstraction work, we thoroughly explored a large number of secure compilation criteria based on the robust property preservation idea. We carefully studied the criteria and the relationships between them. For each of the criteria, we looked at property-free characterization. We proved implications between criteria, which is usually pretty easy, but also we proved collapses or reverse implications between criteria that might seem weaker, but in fact are equivalent to what might seem stronger criteria. And also we proved separation results. So we exhibited compilers showing that certain properties are strictly stronger than other properties. In some follow-up work, we extended this set of criteria in the diagram to arbitrary trace relations, and I'm going to talk about that next. Also our work helps better understand full abstraction and its limitations, and we used proof techniques for full abstraction to also prove our criteria. So the rest of this talk is focused on these last 3 points. So first, about extending this to arbitrary relations on traces, kind of relating source and target traces. And the idea here is that this relation might not be equality. For instance, if your language has undefined behavior, like it happens in ComCert, so ComCert works for C, the relation between source and target traces is defined well. The two traces should either be equivalent or they should share a common prefix M, after which the source trace has an undefined behavior and stops, while the target trace can continue arbitrary. And this captures the idea of, well, undefined behavior in C, in which the C semantics can no longer tell you what happens. It just stops with this goes wrong symbol, while the target semantics continues in an arbitrary way, which is very bad for security, but, well, ComCert is only a correct compiler, is not a secure compiler. And this is how correctness is stated with respect to this trace relation. Another example is resource exhaustion, which is the dual. For resource exhaustion is the target trace that stops because the resources are exhausted, say run out of memory. However, the source trace can continue. In this case, well, simply because you don't have enough information in the source to know when these resource limits are going to be reached in the target. And there are many, many other examples. For instance, the values of the source and the target might be different, and if they appear on traces, then also the traces will be different. Side channels, when you have more fine-grained observations in the target than you have in the source, and also the granularity of events in the traces can generally be different, and there are many more examples. And this is not just about secure compilation. This is also about compiler correctness. The two examples above, ComCert and KKML, are verified compilers, well, for correctness, not for security. So this whole idea is shared among the two, secure compilation and compiler correctness. The main issue in this space is not how you relate traces, but how do you relate properties between the source and the target. Because it's very easy to extend the property-free characterizations, especially for one of our simplest properties, robust trace property preservation, the one we saw before, It's really almost the same as before, just instead of quantifying I mean, here we are quantifying over a target trace, because now we have source traces and target traces that they might be different. However, everything is the same in the premise. But now in the conclusion, we have this extra quantification over some source trace that is related to the target trace we want to back translate. And well, the source program is now allowed to produce this source trace. So this is a very simple extension of our previous property-free characterization. But one might wonder, what does this give us in terms of property preservation? What properties are preserved by this characterization? And here is one way to go at it. You could say, well, all source properties, all source trace properties, so pi s, and you could say, well, if P robustly satisfies some arbitrary source property pi s, then compiled P should satisfy, and now is the problem, right? You have a source property, but you can no longer apply it to the target, so you need to map it to a target property, and this pi tilde is a mapping of source properties into the target guarantee you get if you run the secure compiler. And this can be generically computed, generically defined as the existential image of the relation on traces theta. However, this is not the only property-free characterization, property-full characterization one can give. Here is another one. Instead of quantifying over source traces, we can quantify over target traces. And now we can say, well, what if I want a certain target property pi t? What should be the source obligation I should prove in order to obtain pi t in the target? And this is really dual. It can also be generically computed as the universal image of the relation tilde. And there is a nice mathematics here. These two mappings between properties form a Galois connection. And if you're interested in the detail, you can go look at the paper. Now, returning to our original diagram, so we've extended this diagram also to these relations, but if we talk about the original diagram, one question one might ask, especially given the title of the talk, is where does full abstraction live in this diagram? And we showed that without internal non-determinism, full abstraction follows from one of the criteria in our diagram. And well, maybe more surprisingly, we also show that full abstraction doesn't imply any other criterion in our diagram. And this is not bad necessarily. There are other criteria that are also lives in our diagram, like robust safety preservation, which we've looked quite a bit at, robust non-interference preservation, which the next talk is going to be about. However, still for full abstraction, it was a bit of a surprise that it doesn't imply any of the other criteria in the diagram. But we proved it, and by giving a counter example, which is adapted from a previous CSF paper. And the idea is pretty simple. So if the compiled program detects that the target it links with is malicious, for instance, if the context passes in a bad value, like an ill-type value, what the compiled program can do is some arbitrary bad actions, like launching the missiles, which breaks robust safety preservation, or looping forever, which breaks robust liveness preservation, or leaking the secret inputs it received over the execution, which breaks non-interference preservation. The only surprise here is that this does not break full abstraction or compiler correctness. And for full abstraction, the reason is that this bad behavior, like launching the missile, doesn't really depend on the compiled program. It really only depends on some backdoor we've inserted in the compiler, which introduces these bad actions irrespective of what the source program was, which means on the two sides of this observational equivalence, nothing will change, right? So full abstraction will be satisfied. Also, compiler correctness will be satisfied as well. Generally, compiler correctness only tells you that, only talks about what happens when you link with well-behaved context. While here we are not looking at a well-behaved context. So the takeaway from this is that in general, full abstraction really only ensures code confidentiality, and that's how it's defined. But it does not ensure integrity or safety or data confidentiality. And this counterexample really shows this. Now, the situation is actually a bit subtler because, well, in certain particular scenarios, one can ensure that full abstraction implies, for instance, robust non-interference preservation. Or so it seems from some recent work by Matteo Busi and collaborators. The main idea is simple. Since full abstraction ensures program confidentiality, make the secrets be part of the program, for instance, of the data section of the program. So this is an interesting idea. I think it would be very good to formalize it, even if it's not the most direct way to get robust non-interference preservation. Still, if people make this kind of claims, I think it would be good to formalize them. Another recent proof that was formalized, at least on paper, is the proof by my student Carmine Abate and again Matteo Busi, that full abstraction implies robust hyperproperty preservation with this tilde, yeah? So with a non-trivial relation on traces. The problem here, I mean, this is very nice mathematical work. However, the problem with this in practice is that this tilde relation is defined depending crucially on the compiler itself, which means the compiler is still part of the trusted computing base. So by proving such RHP tilde for this tilde, you really haven't gained much in terms of confidence. The reason people verify compilers is usually because they don't trust them and they want a statement that doesn't, a correctness statement or a security statement that doesn't include the compiler itself, right? The problem though with full abstraction is, my impression is that all full abstraction results have the compiler in their trusted computing base. And I see this as, looking again at a result by Joachim Paro, it really says that for any two languages, there always exists a fully abstract compiler. So if I just give you two languages and I say I have a fully abstract compiler between them, and you don't have to look at it, which would mean not having the compiler in your TCB. The problem is I might be really giving you this theoretical compiler built by Paro based only on cardinality arguments. So I'm not sure what exactly one gains with that in terms of secure compilation by just proving full abstraction. So personally, for me, it's still unclear to what extent full abstraction makes sense as a criterion for secure compilation. However, the good news is that now we have many other criteria that clearly define what properties are robustly satisfied. So our whole diagram. The other good news is that we can prove the criteria in this diagram using proof techniques that were originally developed for full abstraction. We show this for a simple translation from statically typed to dynamically typed language with first order functions and I/O. We show that the strongest criterion in our diagram is achievable by using a technique called the universal embedding. And we also provide a generic technique for back translating finite sets of finite trace prefixes for achieving the criteria in this green part of the diagram on the right. So now, just to wrap up, future directions, it's still open to build secure compilation chains that achieve provably secure interoperability with low-level code in practice. That is for realistic programming languages. This is still a big open challenge. It's always a problem to build more scalable proof techniques in this space. Also, the trustworthiness of the proofs. It would be great if more of the proofs in this space would be mechanized in a proof assistant, as it happens, say, for compiler correctness, which is a much simpler kind of property. And finally, this kind of secure compilation proves that if you have security in the source, you also get security in the target. However, how do you achieve security in the source in the first place? Proving this kind of robust satisfaction is also a non-trivial task. With this said, I'm going to stop for questions. Thank you.